Let's look at the algebra of the interior product. So here's some calculations we did geometrically. Ooh, completely all-important minus sign that I was about to forget there. So if you take dx wedge dy, and this is really in any dimension, but you can think about it in R2 or R3, and you interior product E1 into that, the claim was we got dy. And if you interior product E2, corresponding to the y variable, into dx wedge dy, then you get minus dx, that ubiquitous minus sign, of course, whenever we switch the order of things. And, of course, it's really crucial that it's linear, both in the vector argument and the form argument. It's pretty easy to show by the basic definition, the algebraic definition that I gave a couple videos ago. So let's use that linearity to just figure out what IU on dx wedge dy is, and then I'm going to use that to explain a very, very important algebraic rule for I. So that's just going to be I with this combination of dx wedge dy. Okay, so by the linearity, it's going to be u1 times I e1 of this stuff. So it's just going to be u1 times dy. And then plus u2 times I e2 of dy, but that gives you a minus dx. So if we reorder it, it's minus u2 dx plus u1 dy. Okay. So I want to make a geometric note about this, even though mostly I'm doing algebra here. Let's look, if suppose we're taking dx wedge dy, which looks like this, or of course sort of any rotated version of it. We're taking u looks like this, and this is not just some random expression. This is what I would get if I took minus u2i plus u1j, the vector, and took the one form corresponding to it, the tilde of that. And that's corresponding to the fact that when I do this, the geometry is that I can think of that as something sort of pointing, if you will, perpendicular or rotated. So the I has a bit of a feeling of rotation. It's as if I had rotated the vector u, say r of u as a rotated version of u, and then just got the one form that lines up with this sort of the one form version of that. That's what the tilde operation does. Okay, so that's very interesting. It's also especially interesting that whenever I rotate something, now in 2 dimensions, I don't need to really say anything about an axis of rotation. But if I'm in 3 dimensions, I do have to say something. Rotate about what axis? Well, notice what we're rotating about is the z-axis. And somehow, maybe this is controlling the axis of rotation. The one variable that's not mentioned there is the z variable. And indeed, this is sort of controlling the axis of rotation, and then this is getting rotated by that. And if you know a little bit about how rotations and cross products relate, which I'll talk about a lot in view 3 of the cross product, that's suggesting that the cross product is going to indeed come up, which will very soon. Okay, so now let's look at this equation again. Let me just rewrite it without the clutter. Okay, so this is minus, well, I'm going to rewrite it in the way I had it before. u1 dy minus u2 dx. Okay, and I want to notice something. This is what I would get if I just took IU of dx and then wedged it into dy. So IU of dx is just dx eating the vector u. That just produces u1. Okay, so it's an overly fancy way to write this guy, but it's going to be very interesting in a minute. And then minus, and I'm going to change the order of things a little bit here. I'm going to leave the dx in front, and then I'm going to call this IU of dy. Because IU of dy is just the dy form eating u by definition. That just gives me the u2 component. Okay, this looks very interesting. This looks like a product rule. And in fact, the general rule, and I'm not going to prove this completely for you, but I'll just make some comments about it, is that it's exactly like the product rule for D. IU alpha wedge beta plus minus 1 to the degree of alpha wedge IU beta. In this case, it was a minus because the thing I was passing it over, I was exchanging the order of the IU and the dx from here to here. and it was a 1 form. In general, it turns out you get -1 to the degree, which is a very, very common thing. So this is the point here. Part of the point is to compare to the D. We're not doing a lot of derivatives in these talks because it's really about the algebra forms, but I can't resist comparing this. It's exactly the same rule as this special sign modified product rule, often called the Leibniz rule, for the exterior derivative. So this is actually rather strange and rather deep that I, even though it's algebra, it's acting like a derivative. It's called a derivation of the wedge product. So that's a funky thing, that something constructed purely out of algebra is acting a lot like a derivative. That's pretty cool. So the other thing I want to mention is, let's go back to this for a second. Let's remember the basic algebraic definition. If I take IU of a 2 form, that should be a 1 form, and then I should be able to know what that does to a vector v. Okay, and by definition, that's just dx wedge dy, and you fill up the first slot with u, and then I've already got something to put into the second slot. Okay, if you work that out, it just turns out to be u1 v2 minus u2 v1. It's the determinant of just make those things into those two vectors into a 2x2 matrix. Determinants are intimately connected to wedge products because determinants calculate areas, and this is just the area form. Okay, it's oriented areas, of course. And what I wanted to point out, again, not something I'm going to go into detail on, it turns out that what this is, if you actually prove this in general, one way to prove it in general is to look at it with higher degrees forms. You get bigger determinants, and it turns out this is equivalent to the cofactor expansion of a determinant. So you can prove it using the cofactor expansion, and really it's so tightly connected that we could say that this is actually in a deep way. Oh, sorry, not that one. This one, the IU version. This fact about putting things one at a time, feeding vectors one at a time into wedges, really is equivalent to the cofactor expansion for the determinant. Again, I could go further with that, but there's so many things I could go further with on this. Preparing these talks, it's been fun, but there's so many things you can jump to out of the vector triple product. It's very cool. Okay. So one thing to note is that a lot of people define the interior product just by these three facts. A function dies. A one form just gives you the pairing on one forms and vectors, and then this derivation fact, the fact that it looks like a derivative, it has a product rule. Because if I want to expand out IU on any kind of wedge, then I can just use this to break it down. That's not a D. That's not a D. Just B. Sorry, just beta. I can break down any kind of wedge to smaller and smaller and smaller things by just inductively using this rule. And again, it's actually equivalent to the idea of taking a huge determinant and repeatedly using the cofactor expansion to expand it. Okay. So just a little bit more. Here's an exercise. I'm mainly doing most of the work for you here. But here's part A of the exercise. Show, so it's going to be sort of exemplifying how powerful this is. Show that if you have two vectors and I combine doing the operation IU and IV in both orders and then add, it's called the anti-commutator. Let's say it has the derivation property. So it's an operator that has the same property, but with no minus sign. Okay, which kind of makes sense because we're doing two things, not just one. So when you flip it, we don't actually need a minus sign. Okay. Part B. Show that this particular combination, this anti-commutator, this symmetrized combination of IU and IV, show that this vanishes on both 0 forms and 1 forms. That's actually really easy to show if you think about the degrees, what degrees these things have. Okay. And so C used that to show that, in fact, I guess I should have put vector arrows over here, that IUIV plus IVIU equals 0, period. It's just secretly the 0 operator, okay? Or in other words, if you interior product 2 vectors in one order, you get it in the opposite order, okay? And so that's on any alpha, basically, okay? Part D would be, this is a nice illustration of the power of this kind of definition, but it's actually easiest. You can actually show it from the original definition. It's really just, to check it, it's really just another way to say that when you feed vectors into forms, it's antisymmetric. Okay, and then part E, let me just scoot it in up here so you can see it all on one screen. Part E, pretty easy consequence, is that if you do it twice with the same vector, you get 0. Again, you can either show it from the original definition of feeding things into the slots, or you can show, or it's an easy consequence of this, which comes from this. Okay, so if you do it twice, that's equal to 0. And I just want you to compare to d squared equals 0. Hey, that's another similarity. D is this derivative, it satisfies a product rule, and it squares to 0. For any vector u, interior product with u of a form is another thing that satisfies exactly the same funky product rule with funky sign, and that squares to 0. Lots of cool similarities there. Okay, good enough for this one. Especially since this is just a test, and it might be another frustrating failure.